starting. mm, we are starting senior six. Congratulations for making it to senior six. And so, as per our program as Hope, we always start with a very simple topic. We don't do revision because we come from different schools. So if we start repeating each and everything, we might end the whole holiday looking at senior five work, and yet senior six is also on the waiting. So we have this privilege to start a new topic. I hope each majority, if not all, have not started on it, or even they have started on it. Some few schools might have reached somewhere. That is magnetism. It is a very simple one and very interesting. Don't listen to what others say. Me, I want to tell you the truth. Magnetism is something very simple. Questions are very direct. You just have to open your mind to understand what it is all about. Is that okay? So without wasting time, we shall start straight away. I have some PowerPoint here that we shall be going through. I'll accept some questions or some feedback if there is. My name is Teacher John Bakayana. I'm a teacher. I think that's all about me. Okay, I hope everyone can see. Let me just give permission or chance to one or two people. These will be reading for us messages from the chat. I don't know who has been active in that area. Okay, there is Lynn. So Lynn, you'll be doing the needful because you are the co-host. If there is any message that requires attention, feel free to ask me to hold on. We go through that message. Is that okay? So we are looking at section C, which has magnetism and AC circuits. Magnetism is wider, very big. That's why we encourage that the earlier you start it, the better. Questions that come, like I told you, are very direct. You just have to open your mind. There is a very small subsection of subsection of AC circuits, which some students think it is easier, but in most cases, almost a half of the marks in AC circuits, a half of the marks is from magnetism. That means you need to cover magnetism also if you are to maximize marks in AC circuits. So we build from O level. We assume that you looked at magnetism in O level, but if not, we have a very brief recap of what magnetism is. Yeah, so what's a magnet is a substance that can attract certain materials known as magnetic materials. So when freely suspended, it always comes to rest in the north-south direction. In other words, facing the north and south direction. This we looked at in O level, that simple experiment. Magnetic material types, we have categories. You know those, the paramagnetic and the diamagnetic. Let us remind each other. I want to be somehow slow. Let us remind each other of the paramagnetic and diamagnetic materials. What are they? Any hand? We shall have some kind of interaction, yeah? What are paramagnetic and diamagnetic materials? Yes, did you cover it in O level? Okay, now those who are writing, uh, you are making it hard for me to edit my work here because you are taking over. And okay, what are ferromagnetic materials? We start with that. You can feel free to write in the chat. Uh-huh. I'm seeing a hand here. Okay, you can write in the chat because I'm trying to disable these ones who are just writing anyhow on our screen. Okay. So you can write in the chat.
Teacher John?
Okay. Yes, Mr. Kaziva. Thank you so much. I'm kindly requesting, Mr. Kaziva,
Mr. John?
I'm kindly requesting
Mm.
that make more than one person a co-host because now the other one has taken a lot of time to respond.
Oh,
If they can be
okay.
like four.
Okay.
Mm.
People do I know? Okay.
Okay, meanwhile, guys, let us continue. Sorry for that delay. I went off temporarily and the co-host had to give me rights to continue. So we are sorry for that. Nevertheless, we can continue. Thank you so much. Those that have been sending answers in the chat, I've been reading through. People have been taking us through the paramagnetic materials, the ferromagnetic materials. We also have diamagnetic materials. Like I said that we are having a brief recap. We looked at this in O level. We are simply adding on to what we are going to look at in A level. So thank you so much for those that have been sending answers in the chat and those that have been encouraging us to keep calm. That shows a highest level of maturity of you. So thank you so much. Now let's continue. I'm sharing my PowerPoint. Hope we can all see now. Magnetic materials are classified according to how they respond to magnetic field. We have what we call ferromagnetic materials. These are materials which are strongly attracted by a magnet. The examples are given. We have what we call the non-magnetic materials. These are materials that cannot be attracted by a magnet. We have the examples. Because we don't have a lot of time, I may not remain on a single slide for everyone to write. Maybe if you can just take notes somewhere, but we shall share definitely the notes after the lesson. Okay, we have paramagnetic materials. These are ones which are weakly attracted by a magnet. Is that okay? And I put a note here that magnetism is produced by the motion of electric charges, which cause attractive and repulsive forces. So this kind, we shall look at it in details. That okay? I hope you have taken note of paramagnetic materials, those who were asking what it is all about. Um, Yeah, we are still revising. This is O level. I'm going through a little bit faster because this is O level. Properties of a magnet, like a poles repel and like a poles do attract each other. And that is the basic law of magnetism. The other one is magnetic field lines run from North Pole to South Pole. I hope that you looked at it in O level as well. Magnetic force is greatest at the poles. Yeah, maybe if I can add on something here. Hmm. If this is my magnet, north and south, then from the north towards the south, eh? Okay, we'll have something like that. Okay, now the one who is writing, we shall give you permission, don't worry. So, from north to south, like that, magnetic force is greatest at poles. We talked about that because there are many magnetic field lines, those that are coming in into the South Pole and those that are leaving the North Pole. So because of the many concentration of magnetic field at the ends or at the poles, we expect a lot of magnetic force at those points. A freely suspended magnet aligns in the north-south direction. This you should have looked at it in O-level as well. That simple experiment. Okay. So magnetic field, it's a region of space in which a magnetic force is experienced by a magnetic substance, a moving charge, a current carrying conductor. So there are basically three things that we shall look at that constitute the magnetic field. Number one is a magnetic substance like a magnet itself. We have moving charges. Moving charges also can lead or uh, can give us a magnetic field, and also a current carrying conductor. When current flows through a conductor, there is a region of magnetic field around that conductor. We shall see this in details. You don't have to worry. So magnetic field lines run from North Pole to South Pole. We talked about that. Okay, these, I chose to put them here in summary. We shall look at them in details later. When you look at them, you will have to refer because I will not come back to and flow to the same page. So let us have some little time talking about this, the magnetic field patterns. Number one, we talked about the bar magnet, and we said field lines run from the North Pole to the South Pole. We also see one of the characteristics of these field lines is that they never cross each other. They never cross each other. They concentrate more at the poles. Is that okay? The horseshoe magnet, this is how magnetic field patterns behave on around a horseshoe magnet, concentrating so much on the poles, south and what? And north. Hope that is okay. When two magnets are placed near each other, when they are facing opposite each other, we have some kind of attraction with magnetic field lines traveling from the north to the south. So this is the behavior. However, if they are repelling each other, this is the kind that we get. Is that okay? Creating a neutral point somewhere. We shall see that in details. We have what we call a current carrying conductor. When a conductor, for example, a piece of wire, I say these wires that carry current. When a piece of wire carries current, round it there is a concentric form of magnetic field around that wire. So that's also another form of magnetic field that is around a current carrying conductor. We shall see it in details also. The toroid also, toroid in simple terms, requesting, like I said, okay, to stop AI companion. Do I, okay, stop AI companion. Stopping it makes things better or worse? I'm not a computer wizard, but let me decline anyway. Okay, so let us continue. We have, yeah, I'm picking out the most common ones. The toroid is not that very common as far as what we're interested in, but that is the behavior of the current going in and current moving out. How the field arranges around the toroid, think since it's not part of what we expected to look at in the chapter or in the book, we can ignore that. Let's look at the solenoid. Solenoid, we shall also look at it in details, but solenoid is simply making a coil. You make a coil, then allow current to flow through that coil by connecting to a battery. If it, before it is a simple coil that is connected to a battery. Once you connect to a battery, current flows through that coil. That coil now, it becomes now at every point, it becomes a current carrying conductor. And when it becomes a current carrying conductor, it comes with it a magnetic field. So that magnetic field whose flow is given in the diagram here. We shall not allow people to record because if I allow everyone, I shall have to keep tapping allow. So I'm just letting you know that I'm not giving permission to anyone to record, but we shall get a recording definitely because after all, uh, the session is being recorded. If not yet, I think it's being recorded already. Okay, so when current flows through the coil becomes a magnet. That form of a magnet is what we call a solenoid. Is that okay? It is what we call a solenoid. So there's a magnetic field that comes along that kind of arrangement when you make a coil and then you allow current to flow through that coil. So yeah, check here. It's a magnetic field we are talking about. Okay, the direction of the magnetic field, we shall look at it. Of course, it also depends on the direction of the current. How current goes inside or through the coil and how current comes out of the coil determines the direction of the flow of the magnetic field lines in that solenoid. If you want to say something, you can feel free to put up the hand at the right time. We shall pick you to either supplement, give a feedback, or say anything that you want to say. So we continue. Magnetic field direction symbols. Okay. Now this one is more about the current carrying conductor. Current carrying conductor, I said, can be a piece of wire that carries current either inside something or outside something. When we say inside something, that is something in magnetism, we prefer calling it a paper. So that's why we say the piece of wire is carrying current inside the paper, or the piece of wire is carrying current outside the paper. So that is the simpler way we can visualize it. So if this is, let me try to draw it, to sketch it here. For example, if this is my piece of paper, and then I have a piece of wire carrying current. Let me see. This is my piece of wire that carries current. And of course, definitely, it moves out like that. Let's say that is current. And then this is that's our paper. So let's leave it plain. So if that is the wire carrying, now we consider that when current is entering to the paper, or this one, let's call it the paper. Current is entering into the paper through the wire, then we give it a cross. We give it a circle and a cross. So this one is a physics demonstration that I have a piece of wire carrying current inside the paper. But we shall see that in details later. Also, if we get the reverse is if, for example, to have my piece of paper like that, and then I have a piece of wire. Now this time, current seems to be coming from the paper towards me, assuming that the observer is, let me first name this one as our current. Now, if I'm the observer this side, current seems to be carrying, the wire seems to be carrying current from the paper towards me. In physics, we show that as a circle and a dot. Is that okay? So into the paper, circle and a dot. Out of the paper, then we consider that one as, out of the paper, we consider that as a circle and a dot. Into the paper, it is a circle and a cross. So we call it a paper for simple understanding. But of course, as current carries, as a conductor carries current, for example, of course, this one, we shall see it using the grip right-hand rule. If a conductor, like a piece of wire, carries current, like we saw, around it is a magnetic field. And that magnetic field is a circular magnetic that magnetic field is a circular magnetic field. So the direction of the magnetic field, is determined by the grip right-hand rule. So we shall see the grip right-hand rule. Yeah, that is it for that page. Now, magnetism of a current carrying conductor. This is now what we've been demonstrating. That if you connect a battery, connect wires, then allow current to flow this wire. Allow current to flow through this wire. This is our switch. We normally, you know how we represent a switch, the better way. But allow current to flow through this wire and then through the paper. This is the paper. Now we can have a pointer or a simple magnet compass. This one can give us the direction of the magnetic field because we said if we are using the iron filings show the presence of the magnetic field lines. They don't show you the direction. Iron filings can arrange themselves in a circular pattern to show that actually the magnetic field lines around this current carrying wire or current carrying conductor are circular. If you want to know the direction, then you can use a compass needle. So the compass needle points where the direction of the field is going. Is that okay? Yeah. Now, I don't know if you'll be able to see, um, able to see my hand? Because now this requires some kind of practical. Let me first stop sharing. Okay. Yeah, I think you can see me, eh? So I want to demonstrate this. I have a pen here. Let's take the pen to be the current carrying conductor. Let's say that the tip of the pen shows us where the current is going. Then the bottom of the pen or the cap shows us where the current is coming from. Is that okay? Now I hold the pen like this. Hope you can see from this side. This is how I'm holding the pen. Now, the thumb points in the direction where current is going. The thumb, if you have a pen, you can also demonstrate. The thumb points in the direction of the current. In other words, the thumb shows that if this pen represents a conductor that is carrying current, then the thumb points that current is actually moving upwards. Now, the direction of the rest of the fingers give us the direction of the magnetic field. Hope you can see. So the circular pattern that you see around a current carrying conductor is actually the pattern of these fingers. So if I point up like this, then the fingers show me that it is, which direction is this? Anti-clockwise. So this is anticlockwise. So this shows me that if current is carried in a conductor, which is a pen, for example, upward can be out of the paper, then the direction is anti-clockwise. If I can show you, anti-clockwise. Of course, you can demonstrate it with your hand. Now, this is what we call the grip right-hand rule. Grip from the word gripping something, like I'm gripping a pen. Now, what happens? Now, this is out of the paper. Into the paper is actually turning the pen upside down. If I turn the whole demonstration upside down, I'm now showing that the current is entering into the paper, as showed by the thumb. Then you notice the direction of the fingers changes. It was anti-clockwise, it is now in clockwise direction. Now in clockwise direction. So that means that when we reverse the direction of the current flowing through the conductor, the magnetic field around that current carrying conductor also changes. When it was pointing upwards, it was in anti-clockwise direction. When it changes to point downwards, we see now that it is in clockwise direction. So this is how we demonstrate the arrangement of the magnetic field lines around a straight wire carrying current either out of the paper or into the paper. Okay. Has someone picked something? Okay. Uh, Yeah, let me just repeat this one. Assuming that this pen of mine is the one that is a piece of wire carrying current. Now the current is moving from the cup. The cup is this bigger part of the pen. The tip, the writing point, is the smaller part of the pen. Now, we say that, let's assume current is coming through this wire. Now, I'm using a pen as a piece of wire. If current is flowing through this wire from the cup through the writing point, I will hold or grip what we call now the grip right hand rule. I use my right hand to grip this pen. I grip it in such a way that the thumb points in the direction of the current. Focus so much on the fingers. So these fingers will give you the direction of the magnetic field around this conductor. So the pattern is that where the finger faces gives me the direction of the magnetic field. If the fingers are facing this way, for example, I'll follow that to trace the direction of the magnetic field. So this means that if I'm pointing or I'm allowing current to move upwards, remember we represent that with a circle and a dot. If it is upwards, then we say the direction of the magnetic field is anti-clockwise, following the direction of the fingers. Now, if I want to know what happens if the current carrying conductor is going downwards into the paper, I simply turn my hand upside down. When I turn the hand upside down, we see the direction of the current is moving downwards this side, or what we call into the paper. Now, the direction of the fingers now changes. It was anti-clockwise. Now, when you see, it is coming into clockwise direction. So how do we conclude? That when current is flowing through the conductor inside the paper, the field pattern around that current carrying conductor flows or follows a clockwise pattern or clockwise direction. This is very important, like we shall see in daily life applications as far as physics is concerned. Okay, so I can pause at that and then we continue with our work. Let me go back and share. That is important to know at as early as this. Yeah? So following this, now because so this is what we have. I hope I can't see myself now, but I hope you can see. This is what we have. This is my pen. I grip it. Upward means out of the paper. That is our paper. And also, let me show our paper here. Yeah. So this is our paper. We have the conductor carrying current. Conductor is a piece of wire. It is carrying current through the paper upward like that. And what is the direction of the magnetic field? We said there are two ways. You can use the needle, the compass needle, or you can follow what I'm calling the grip right-hand rule. So these arrows are the ones that are represented by the fingers when I was demonstrating, or when you are demonstrating. These are the arrows that we see, our fingers. So this is how we visualize it. But we are going to see it later in some other diagrams. Is that okay? So this is what I've been explaining. We have two ways of determining the direction of the current around a current carrying conductor. We have two ways. One way is the Maxwell corkscrew rule. Another one is the grip right-hand rule. Maxwell corkscrew rule, because I don't have a screw here, I'll not take us. Yeah, but when you know that when you want to enter a screw into something, when you turn clockwise, it is entering. It is getting inside. When you turn anti-clockwise, it is coming outside. So that concept also gives us an idea on how to determine where the turning represents the direction of the magnetic field, then the direction of the screw, that screw is getting in or out, that's the direction of the magnetic field, whereas outside gives us the direction of the current. That is a Maxwell corkscrew rule. What I've explained here is the grip right-hand rule, which we have seen clearly here. So we've just seen that if I have a current carrying conductor, hmm, okay, draw another one here. So I drawn another wire carrying current. Now we are terming it the current carrying conductor. This one is moving now downwards. So the one moved by upwards, that is out of the paper, a circle and a dot. A circle and a dot. Then inwards, that is into the paper. We said we represent it by a circle and a cross. So this one is a circle and a cross. This
Someone
one
gave
is,
an
yes?
example of a bottle. Someone gave an example of as in opening and closing a bottle. Could it also work?
Opening and closing a bottle. It doesn't work
Mm,
because why the screw thing
mm.
work is that with a screw, two things are happening at the same time. As it rotates, it either moves inward or outward. But when you are opening and closing a bottle, you are just opening and closing, nothing else happens. So that one doesn't show the movement of the current. Whereas for a screw, as it moves inside or outside, we see the movement of current. At the same time, we see the movement of the field, or we see the direction of the field. You get the difference? Yes? Because the two have to work concurrently. Okay, so now here we are having, according to the grip right hand rule, if you now the rest you have to figure it out because this should also be somehow practical. Maybe I'll show a video and we'll watch. Yeah. So if I'm having current out of the paper, the direction is anti-clockwise. You should also be able to get it when you sketch it with yourself. Then into the paper, the direction is in clockwise. Into the paper, the direction is clockwise. So that's something I'm trying to say, but we shall see them in details. We shall see them in details. Kale, Maxwell corkscrew rule is here. We are saying that imagine a corkscrew turned in the direction of the electric current. In the direction of the electric current. This is what I said, that if you have your screw and you start rotating it. So as you rotate it, it moves either inside or outside, depending on the direction. Is that okay? So when you rotate it clockwise, it is getting inside. When you rotate it anti-clockwise, it is getting outside. You get it?
Yeah, we get it, but
Yes?
someone says that the network to people sharing the two screens. People are saying it's lagging their network.
That what?
That the two screens, it's making the network to lag, kind of being unstable.
My what?
Your network,
My network is not stable, eh? Oh.
and it's because you're sharing two screens. So
Oh, okay.
maybe
I'll resolve
you leave out that of yours, and
the
then
video.
let me have the one showing work.
Which other one should I close?
That's it. You're clear now.
Okay, because I've also been seeing unstable network. I didn't know what it was. I didn't know the cause. Okay, so now that is the grip right hand rule and the Maxwell corkscrew rule. I said Maxwell corkscrew rule is also more or less the same as the grip right hand rule because it entails both the movement of the screw and the direction of the magnetic field, just as the grip right hand rule does. Okay, imagine a corkscrew turned in the direction of the current. That is, for example, if the screw is entering into something, we say current is entering into that something. And of course, as it is entering, there is the rotation of you call them what? Those sharp points on the screw. Do we call them edges?
Like strips, all threads.
Threads, yes, the thread. So those sharp points on a screw. When the screw is entering inside or coming outside, the threads are rotating. So that direction of the rotation of the thread gives us the direction of the magnetic field. Is that okay? Kale, this is what I've been demonstrating with the grip right-hand rule. For those who didn't get it better, now you can see it. The thumb points in the direction of current. The rest of the fingers point in the direction of the magnetic field. For example, in the left-hand side, we see that where the thumb points upwards, the rest of the fingers point, the direction is now given to us. We can clearly see that that is anti-clockwise direction. Is that okay? And so we can relate with the concentric direction of the magnetic field pattern around this current carrying conductor. I think we can visualize it now. So on the right, we say this one is the same as on the left. It is the same as this one. So when we turn the hand upside down, now the direction of the magnetic field changes, becomes clockwise. You remember the same as the Maxwell corkscrew, that as you are entering the screw, the thread direction is in the clockwise direction. And when you are removing it, now you are removing it in anti-clockwise direction, but it is actually coming out of the paper or out of what you are intending to get it out from. Are we picking something?
Yeah, we are doing so, teacher.
Okay. Now we can't talk about magnetic field and we don't talk about magnetic flux. Magnetic flux now is the total number of magnetic field lines linking normally the plane of a conductor or coil. Now we are starting getting a little bit more than what we looked at in O-level. I underline the word here that is very important. Students make a mistake, most especially on this word here. Let me even use a red color to emphasize this one. The word is linking, not leaking. Leaking. Some students use this. Now, this one is not correct. As far as this definition is concerned, this one means okuyika. Ate this one means okuyitamu for those who understand Luganda. So we are using linking because if this is my figure and then we have magnetic field patterns or magnetic field lines going through that. So the word going through in physics, we use linking. So if this is a conductor, and this is my magnetic field line, then we say it is linking a conductor. If it is going through at 90 degrees, then we say it is linking normally the plane of a conductor. Is that okay? So better to understand. And if you want to understand magnetism, it is important that you get from the beginning because magnetism, one thing follows the other. If you miss out on the foundation, this missing, the introduction or the missing work, later it will be hard for you because now the word linking will be, at one point we shall use this one. Now we are using this. So if you don't understand this first, you'll confuse it with this one, the linking. You confuse it with linking. So linking is when field lines go through a conductor. That's linking. For now, we are not interested in this one. So magnetic flux is the total number of magnetic field lines linking normal at 90 degrees to the plane of a conductor or a coil. The SI units are Webers. Sometimes we write it as WB, Webers. Yeah, those are just SI units. They shouldn't confuse you. Okay, perhaps maybe someone who discovered them or who used them first or who brought them to be used in physics. Those are SI units. Okay, now That's magnetic flux. So this is now a more detailed diagram or structure of magnetic flux. So magnetic flux, when we consider, just pick out one. Let me draw something here. For example, if this is my plane of a conductor, and then this is the other time the definition considers that the magnetic flux is linking normally the plane of a conductor or at 90 degrees to the plane of a conductor. But practically, these magnetic field lines can flow from any direction. Can flow from any direction. They can be at any direction. So for us, what we do in physics to maintain the application and the calculation, we shall still consider the component of this magnetic field line that is normal to the plane of the conductor. So if, for example, this is my plane of a conductor, let me draw it like this. Just draw some simple thing like that. If that is my plane of a conductor, and then this is my magnetic field. Sorry. So, uh, so, minute. So, if this is our conductor, then we have, let me see. Okay, that's a magnetic field line. We can just pick one. So, as per the definition, we shall consider the component. We shall consider the component of this magnetic field line that is normal to the plane of the what? That is normal to the plane of the coil. Now, If the magnetic flux is phi, if the magnetic flux is phi, we have another thing called magnetic flux density. Magnetic flux what? Magnetic flux density. Its definition is here down. Is the number of magnetic flux lines or number of magnetic field lines linking normally at 90 degrees a unit area. That is magnetic flux density. So when you get more magnetic field lines and combine them together, they form what we call a magnetic flux density. Is that okay? So if it is simply one, we can just call it a magnetic field line or a magnetic flux lines. But when they become many and they are linking a certain conductor at 90 degrees for every unit area, then we call those number of field lines magnetic flux, or they constitute a magnetic flux density. So if B is the magnetic flux density, and then we represent all the magnetic field lines with the B, that's a bunch of field lines linking normally a unit area at 90 degrees. But we said that we need component. For example, each of these ones has got a component that is at 90 degrees. Each of these ones, I'll say, for example, this has a component which is normal to the plane of the coil. Even this one has a component which is normal to the plane of the coil. This has a component which is normal to the plane of the coil. This has a component which is normal to the plane of the coil. So all these ones can have angles, same angles. Same angles we are calling theta, just like this one. So we are picking out just one magnetic field line that we are considering, whose angle is angle theta. Whose angle is angle theta. So how do I resolve this one normal to the plane of the coil? Remember, this one is the plane of the coil. If I want to resolve this B to the plane of the coil, it is going to be B cos theta. B cos theta. You understand that? It is going to be B cos theta.
Yeah, we do.
Okay. So from the definition, from this definition of magnetic field line, yes? From the definition of the magnetic flux density B, the number of magnetic flux lines. Remember, magnetic flux is represented by phi. The number of magnetic flux lines linking normally the plane of the coil. In other words, the definition of magnetic flux density is phi over area. If I make phi the subject, I'll have magnetic flux density times area. But for cases where the flux is not linking normally, we need a component of the field line, or the component of field lines which are normal to the plane of the coil. So instead of B, let me write it here. Look more organized. So we've said that from the definition of magnetic flux density, which is the number of magnetic flux lines or field lines linking normally per unit area, flux can be B, that is magnetic flux density times area. In cases where the flux are linking the conductor at a certain angle theta, then phi is going to be the component of B, which is normal to the plane of the conductor, that is B cos theta, then times the area. Sometimes we can rearrange it as BA cos what? Cos theta. Is that okay? So what happens if theta is 1? Yeah, what happens if theta is 0 degrees? Theta is 0 degrees only if this, what makes theta to be 0 degrees is when the magnetic flux density all the magnetic field lines are actually going through the normal like that. You see, parallel lines have zero angle between them. So when theta is 0 degrees, it means the flux we are linking the conductor at 0 degrees. Is that okay? Okay, so when theta is 0 degrees, that's when now we get our phi as b times a, because cos of 0 is a 1. And this is why now the definition makes a lot of sense. Okay, that is magnetic flux. The explanation, the diagrams, and the formula. We shall use them as we proceed. Anything, any questions so far? Or suggestion? Okay, Francis. If there is a co-host, you can allow them to say something. Chirao Par. Hey.
Yes, teacher. Good afternoon.
Yes, sir.
I would like to explain to me more because I've understood something, but I would like to clearly explain to me more about the magnetic flux density and of which is the coil and which is the current on the diagram. So I'd like to explain to me clearly again.
Okay.
Yeah.
Hmm. Which is the coil and which is the diagram? Okay. Like we said, the coil can be the current carrying conductor, because current can be carried in different materials, of course, the conducting materials. A coil is just like any piece of, just like you have, just like you have a piece of copper wire and then you wound or wind. I don't know which one is the past or present tense. Get a piece of wire and make those windings, yeah? Connect to a battery. You have made a coil. You've made coils. In other words, if you just pick one of these windings, one of these seem to be circles, you have something like that. You have something like that. So that's what we call a coil. And current can flow through that coil in a direction. Now, this is a coil, not the direction of the magnetic field. This is a coil. As a matter of fact, these ones are not meeting anywhere like a complete circle. Someone would take it. Now, I would do something like this. I'll say if you bring your piece of wire, then start. Hope everyone has ever done this. Current enters into that coil and current leaves. Is that okay? Now, with these windings, they form a plane. They form a plane. Is that okay? Now, this plane constitutes a magnetic field. Now, magnetic field lines start flowing through this kind of just like we saw that in this, when you connect a coil to a battery, it becomes a solenoid. So solenoid means that there is the induction of magnetic field. You don't have to call them, they bring themselves automatically. So they are magnetic field that come courtesy of the coil that is allowing current to flow through it. Likewise, when you rotate a coil in this manner, like this, allow current flow through that coil. Also, there is going to be a magnetic field. This time, the kind of magnetic field that is flowing can be like that. Is that okay? So that can be the direction of the magnetic field. I think yellow. Is yellow coming out well? So much as I'm drawing them like this, but they enter from one side of the coil through the coil to the other side. So this kind of arrangement here is what we are having here. The coil is that black, then the magnetic field lines are the yellow ones carrying current. And we are saying that these are not always practically normal to the plane of the coil. Sometimes they meet the plane of the coil at a certain angle. But for us, we say the standard definition of magnetic flux density is all the magnetic flux lines. All the magnetic flux lines. Now, this is the definition that if you can get all the magnetic flux lines, if this is the plane of the coil and the magnetic flux lines, all of them meet. That's why for us to show that they meet at 90 degrees, it is easier to use something like this because it brings out the idea so well, though theoretically. So this is the best way to achieve the fact that field lines can link a plane at 90 degrees. A circle practically doesn't come out, but here we can easily see that these magnetic field lines are actually meeting at 90 what? Actually meeting at 90 degrees. Meeting at 90 degrees. So if we are to combine, all these ones, sorry. If we are to combine all these ones, and they are meeting the plane of the coil. Now this is the plane. If they are meeting the plane of the coil at 90 degrees, then these are termed to as the magnetic flux density. The word density comes from relates with area. So they are meeting the plane of the coil per unit area at 90 degrees. That's the summation of all the magnetic field lines. Is that okay? So magnetic flux density is those number of field lines linking a coil, the plane of the coil, at 90 degrees per unit area. So from this definition, we can get the magnetic flux, which magnetic flux is the magnetic flux density times area. So from this, I can also deduce, or I can also come up with some other consideration. For example, if the magnetic field lines are not meeting at 90 degrees, then I'll get the component which is normal to the coil. Like we said, if, for example, we have our feed rate somewhere down here. If this is our plane, and let's say these are our field lines. This time they are parallel, but not meeting at 90 degrees, yeah? So for us, we shall consider still the component that is normal to the plane of the coil. That component can be obtained by resolving. I hope you learned resolving. In A level, you should have learned resolving, but now, did you learn resolving components? If you didn't, then we have issues here. So we shall get, if these are magnetic flux density or the field lines that are linking, we are considering the components that are normal to the plane of the conductor. So we are considering for each, we find the component that is normal or that meets the plane of the coil at 90 at 90 degrees. So blue represents the component that meets the coil at 90 degrees. So we can even feel free to resolve. Like I said, if you have not covered resolving in mechanics, uh, but you'll get it, don't worry. So the component, if this is my B, of course, B for every, I just write B to represent the magnetic field lines because these ones move in the same direction. Resolving one means I'm resolving all of them. So if this is B and this is angle theta, then this component becomes B cos theta. So my formula becomes, instead of B, it becomes B cos theta, then times area, which I can also rewrite as BA times cos theta. So you can take note of this formula. It is very important. We shall use it in some other coming applications. Okay, let us continue. The formula is here down. Fail to capture it well. Now, there is something that is very important that, remember I've told you that when we are making a coil, yes?
Good afternoon, sir.
Good
I
afternoon.
before we proceed, I had only two questions.
Yes?
Number one was what if the flux lines are simply parallel and not linking to the plane? Would you still use the formula that you've given us? And another question is if the flux line link the plane of the coil at 90, like wouldn't the magnetic flux be like zero because cos of 90 is always zero? I was requesting for more clarification on that.
Yeah, thank you so much. Such a very good question. Actually, all those are those are the things that are just here. You simply substitute theta with the angle that is given. As simple as that. As simple as that. So what you're asking, the response is actually here. We are going to go through them briefly. But I was saying that in any coil, when you are making a coil, the choice is yours. You get a piece of copper wire, you can choose to make one wind like that, allow current to flow through. That is a coil, but it is a coil of 1 turn. This is one, that is 1 turn. Is that okay? Now you can choose to get a piece of copper wire and make 2 turns. That is the first one. Rotate it again. That is the second turn. So current flows.
Hello.
Yes?
So I have a question,
Hmm.
but on the other previous screen,
Hmm.
like when the fields have entered the coil,
No.
so after leaving, is that the phi you are talking about, which makes B equals to cos theta, that angle it has made? Oh,
That what?
like the fields are coming from the coil. After
Hmm.
they make that angle, which is phi, which is equal to, is that phi is the angle that after leaving the coil, is that the angle you are trying to tell us that it is phi?
Angle is theta. Phi is the magnetic flux. Is the symbol for magnetic flux.
Oh,
The field lines that are linking the coil. That is phi.
okay, so
Hmm. The angle they make with a coil, that is a theta. So I'm talking about the number of turns. These are 2 turns. These are 2 turns. Now, if you choose to make your coil 1, 2, 3, how many turns are those? Those are 3 turns, not so? Now, that means that for any coil, there can be a number of turns. There can be a number of what? A number of turns. Therefore, if we are working out the magnetic flux, which is the number of flux linking a coil, we don't know how many they are, then we can say N times B times A. So N can mean the number of turns through which you have made that coil. It can be 1, can be 2, can be any. So someone talked about what happens if, for example, what happens if the flux is linking at what? Okay, if the angle is 0, if theta is 0, we said it means that's a point when the field lines are linking the conductor at 90 degrees. Hope this is not confusing. When theta is 0, you take note of it. When theta is 0, it means the conductor, I mean the flux or the field lines are linking the conductor at 90 degrees, because we said we measure that angle between the normal, and the direction of the magnetic field line. Is that okay? So if the normal is also the same as the direction of the magnetic field line, then the angle between the magnetic field line and the normal is 0. That means our formula becomes phi equals NBA, you know where N came from, cos theta, then theta, phi, this is phi, magnetic. So if theta is 0, this will be NBA. Now, what does that mean? Take note of this, that the number of magnetic field lines are greatest when theta is 0. In other words, when the field lines are linking the conductor at 90 degrees. And what happens if theta is 90? If theta is 90, that means if this is my conductor, and let's say this is the normal. I said theta is the direction between the normal and the direction of the magnetic flux line. So that means that if theta is 90, it means the flux lines are going through the conductor like that, such that the angle between the flux line and the normal is 90 degrees. I hope people are following, and I don't want to leave someone behind. So I'll name these ones the normal, and then this one the. So I'll name this one the normal. And then this one is the flux or magnetic flux or field line. So where the normal and the field lines, the angle between them is 90 degrees. Okay. Angle is 90 degrees. That means our formula becomes what now? Phi, which is NB A cos 90. Cos of 90 is 0. So phi is going to be 0. 0 degrees. So what do we note here? We get 0 magnetic flux lines when the angle is 0. Or, I mean, when the angle is 90. When the angle is 90. So when angle is 90, we get 0 magnetic flux lines. Hope we've taken note of that. So flux is equal to 0 at theta is equal to 90. And we've said maximum flux is obtained when theta is 0. Hope you know the difference in these angles when theta is 0 and when theta is 90. Also, we take note still from our formula. Flux is NB A. We said where the number of turn is a 1, then flux is equal to BA. Hope that one is okay. Are we following? Is someone picking something? Okay, I see a hand. Maybe let us try out some questions here to get it better. Let's try out some questions here. This definition, I've talked about it. Let us try out some examples here. Find the magnetic flux linking a circular coil of any turns. Radius is that in a magnetic field of that when the coil is at right angles to the magnetic field. So when the coil is at right angles to the magnetic field, we've even done it here. Let us just follow through. So our formula is NBA. I hope you know that. NBA cos theta. Now, the area is pi r squared, which we have as that. We are given. We have the area here. Now, the magnetic flux density is given as Tesla. Tesla for magnetic flux density. When you're writing it in short, use capital T. We prefer you write capital T instead of writing it in full Tesla. Just write T. That is the unit for magnetic flux density. So, area is given, the angle. Take note that when the at right angles to the field, theta is 0. I hope people are not confused about this. I spent a lot of time explaining that.
Excuse me.
In a magnetic field B, when the coil is at right angles to the field, angle is 0. And that means when angle is 0, because when the coil is at right angles to the field, this is what we mean. If this is our coil, the field is that. So these meet at 90 degrees. So when the field and the coil meet at 90 degrees, it means angle theta is 0 because angle theta is measured between the normal and the direction of the magnetic field. So there it is 0. So we expect our answer to be work out NBA cos 0. So that's what we get. At 60 degrees. Now here, what happens if this is my my coil, the coil makes an angle of 60 degrees with a field. Pay attention to this. At 60 degrees, at an angle of 60 degrees to the field. When the coil is at an angle of 60 degrees, an angle of 60 degrees to the field. Uh-huh. I think this one I need to check it. Okay. Let us see, because I don't want people to get confused here. If this is our coil, now the coil is making an angle of 60 degrees with a magnetic field. An angle of 60 degrees with a magnetic field. If I'm to draw my normal like that, then this angle between the field and the normal is 30. So this was supposed to be 30. Meaning that if I'm to say phi is equal to NBA cos of theta, then the number of turns is given, which is 100 times the magnetic flux density. The area is given. Okay, since we already have them, let me focus on what is challenging us here. So I know the number of turns, I know B, I know A. Now, cos of theta, which theta is this one? This is what I wanted to emphasize. That if the plane of the coil makes an angle 60 with the field line, it means the angle between the field line and the normal is 30. So we shall use 30 here instead of 60. That's a simple correction. You understand? Yes?
Teacher, good afternoon.
Good afternoon.
So, teacher, I'm inquiring about some small thing. You've emphasized at an angle of 60 with. So, is it different from what is in the question that has at an angle of 62? Are they different or it is the same thing?
An angle of 60 degrees.
With, is the with and to different?
They are not different.
Oh, so it is the same thing. So for this case, we are going to use 30.
We are using 30 because if I say that the plane is at an angle of 60 to the field,
Mm.
an angle of 60 degrees to the field, so it is this angle. But remember, for us, we always measure between the field and the normal.
Mm.
So that makes this angle what? 30, the one that we use.
Okay, now, teacher, for which cases do we have to use 60?
Of course, we have used it because it has, we got 90 minus 60 to get 30.
Okay.
Now, where we shall use the angles, okay, that one we shall see it later. But here you just have to understand that we are considering the angle between, such that if the one given is between the plane and the field, then automatically we say 90 minus that to get the one between the field and the normal.
Okay.
So the angle 60 has helped us to actually get the angle between the field and the normal. Is that
Okay,
okay?
teacher. Yes, teacher.
Okay.
So, good afternoon, sir.
Good afternoon.
My question is, are we restricted to only using cos when resolving that formula? Because from that diagram, it is 60 degrees to the flux is 60 degrees to the plane, not so?
Mm, mm,
But then we want to resolve that,
mm.
we want the component of we want the horizontal component, not so? Which is the
We want a
normal.
company that is normal to the field, to the plane.
Isn't it similar to the horizontal component of that field? Because if we are to resolve it horizontally, we can using 60 because it is
Mm.
that 60 is to the horizontal. We can't we use sine 60 like sine 60 being the same as cos of 30?
Yeah, sine 60 is the same as cos 30. Yeah,
Okay,
it's the same.
we are
It is
not
the same.
restricted to.
The concept, yes. I just want us to know the angle that we are considering, because later when you are looking at some other concept like force, we shall be using sine for some reasons. So I just want people to understand this concept that here the angle is between the normal and the magnetic field. But when it comes to the mathematics, it's okay to resolve using sine. But here we are considering the
So
angle
what you
between.
say,
Hmm?
what you're saying that here we should use cos when resolving.
Yeah, let us use cos. I know when you use sine, you can get the same answer, but we shall see another application, another concept where we shall be using cos. People will start confusing. When do I use sine? When do I use cos? So here we use cos so that in case you have an angle 60 between the field and the plane of the coil, you can still get 90 minus that 60, you get the one that is required. We maintain the cos. Because when we go into some other concept of the force, then we shall apply the sign with the reasons.
Okay, sir, thank you very much.
I don't want people now to get confused. Kale, let us try out this one also. A rectangular coil of 50 turns.
Teacher, I would like to ask, what does WB mean?
Weber's units of magnetic flux, just like you
Okay.
have just like you have any Newton for force.
Okay, thank you, sir.
Now the other one was circular, this one is rectangular. So n turns dimension. Of course, these ones gives you the area. We have the number of turns, we have the magnetic flux density. I have the area, which is here now. So I use my formula, placed at right angles to the magnetic field. I say that we need to take note of this when they say the coil is at right angles to the magnetic field, it makes the angle 0. Makes the angle 0. So just substitute and get your answer. Now, here is the case. Here is the case, rotated through 30 degrees. Let us check on this and we see what happens here. If this is my plane of the coil, and at first, the plane of the coil and the field are at 90 degrees. So I'll have they're at 90 degrees. Altogether, so if I rotate the coil through, if I rotate the coil through 30 degrees, I want someone to pay attention. Why it is not working out the way I want it? Okay, just use lines. If I rotate it through 30 degrees, okay, I rotate the coil through 30 degrees. This is my 30 degrees. So what is going to be? Of course, once you rotate the coil, the normal to the coil also changes. The normal to the coil also changes. So this becomes the normal to the coil. So the new normal, now it's not a straight line. So that's the new normal. That's the new normal. Now the question is, what is the angle between the normal and remember, the magnetic field line, which was originally this one, has not changed. Has not changed. So what is going to be the angle? If that is our direction of the magnetic field line. So if this is 30, this angle is going to be what? That angle is going to be 60. Now, which angle is this going to be? This angle is going to be 30 degrees. So that means the angle between the field line and the normal is 30 degrees. Do you understand that? Yes?
So, teacher.
Yes, please.
So, teacher, now where are you rotating from? Are you rotating from this red rectangular coil, or I don't know where you're rotating from? I'm not understanding that part.
Okay. The rectangular coil of 50 turns and dimension is placed at right angles to the magnetic field. So it's placed at right angles to the magnetic field. That's the red is the original diagram.
Yes.
So the red is the original diagram. Then there is a straight horizontal line which shows the normal. Now, previously, through that very normal is where there is the direction of the magnetic field, because it was at right angles to the magnetic field. So previously, the red line, which is normal to the plane of the coil, red, is also the direction of the magnetic field. Now I rotate this coil through 30 degrees. If I rotate it through 30 degrees, the blue represents the new, now the new position of the coil. Are you following?
Yes, teacher.
Let me say this was the original, and then this is the new position of the coil. So when I rotate it through 90 degrees, it means the normal also, because the normal to the coil also changes. So the normal to the coil is this is the new blue line.
Yes, teacher.
Now, what is the angle between the new blue line and the blue? I mean this blue stripe or the blue coil. It's 90 degrees. So that means the horizontal line and the blue coil, write it here. The horizontal line, which is the original position of the field, and the new position of the coil, the rectangular coil. The angle between them is 60 degrees. Why? Because this was rotated through 30 degrees. And remember, the whole of this is 90. So if this is 30 degrees, it means the remaining angle is 60 degrees. So if this is 60 degrees and the whole of this is 90, it means the angle between this new normal and this horizontal line is 30. That means the angle after rotating, the angle between the remember the field line didn't change, it remained. So the angle between the field line and the new normal is 30 degrees.
Mm.
You understand?
Sure, fairly, but okay, why aren't you considering the 90? Why are you specifically considering only 30 and then 60 on the other time? Like, I'm not understanding that part.
Auntie, when we are finding the magnetic flux, remember the definition of magnetic flux density was the number of field lines linking a coil per unit area at 90 degrees. So at first we had, this is what we had at first. The same position of the normal was the same position of the magnetic field. Now maintaining this direction of the magnetic field, but changing the position of the coil. When you change the position of the coil, when you rotate the coil, automatically even the other side does what? It rotates from position 1 to position 2. When you rotate it through 30 degrees, the normal changes, but the direction of the field remains the same, doesn't change. But the normal follows the position of the coil. So if this is the new normal to the position of the coil, it makes an angle with the original direction of the magnetic field. So what is that angle? So that angle, we've been looking for it in this way. That if this,
Wait a bit. So you mean the magnetic field does not change?
no, it didn't change according to the question.
It's only the coil that shifted.
Yes.
Okay. Shall you proceed?
So if the magnetic field does not change, keep it
So,
horizontal.
I
Yes.
also have a question. Like, why are we considering the clockwise rotation, not anti-clockwise?
You'll get the same answers.
Even if I rotate it in the anti-clockwise.
Yes, you'll get the same answers.
Okay, thank you, sir.
So if I rotate through 30 degrees, this is 30, automatically this was horizontal. So the remaining angle here is 60. But I'm not looking for this angle. I want the angle between this horizontal field and the new normal after rotating. So if this is 60 and the whole of this is 90, that means this remaining angle is 30. So that's the angle I've been looking for.
Okay, teacher, I've understood it. Thank you.
Okay. Though what I discourage is people to just cram that because I have 30 here, therefore I should put 30. You shouldn't just cram. You should understand why the 30. Because actually this 30 is not the angle of rotation of the coil, no. Understand that it is the angle between the normal and the magnetic field lines. Is that okay?
Yes, teacher.
So this is how we write the final magnetic flux after rotating. Final magnetic flux, which we have as this, and the answer has been got as this. But remember, the initial one before rotating was computed. Initial one was which one? Was this one. So to get the change in magnetic flux, is going to be the initial magnetic flux minus the final magnetic flux, and you get that.
Mm.
Is that okay?
Yes.
Maybe someone can copy down something, though time is against us. Hopefully I will share this and you go through slowly. Okay,
Excuse
I
me,
want
teacher.
hmm,
So the question wanted the change in magnetic flux or magnetic flux when the coil is rotated through an angle of 30 degrees.
yeah, they wanted magnetic flux, but I'm adding on this part just for you to get, because later as we progress in magnetism, they'll be requiring for that change in magnetic flux. I actually wanted this one, the final magnetic flux, but I'm just adding on another part. In case they ask for the change in magnetic flux, it is always the initial minus the final.
Okay, sir.
So,
Okay, teacher,
hmm,
I wanted you to just clarify on what WB is in full.
Weber's
Okay, the SI unit for sig.
magnetic flux,
Okay, thank you.
Weber's like that, OWB, units for magnetic flux.
Okay.
Kali. Now let's check through a second part. Rotated through 90, let us also understand this. If you rotate through 90 degrees, what happens?
For me, I still didn't understand where the 30 degrees came from.
Now we've gone past it. You are still processing.
Okay.
Okay, pay attention to this one. You will get the concept here.
Okay, sir.
Now this is previous when the coil, it's a rectangular coil. When the coil and the field are at 90 degrees, that is what we have. Okay. When they're at 90
Okay.
degrees, it means the field is going through the normal to this. The field is going through the normal. Let me draw the normal using, unfortunately, I don't have the line.
Okay, sir. Thank you.
Yeah, you can mute. I'm going to go slow here. So let me use blue for the normal here. So the blue represents the normal, but still it is through the normal that this field is going through. Because they are saying that the field and the plane of the coil are at 90, they're at 90 degrees, something like that, 90 degrees. And when they're at 90 degrees, the angle is zero because the angle is between the normal and the direction of the magnetic field. It is zero. So now what happens if I rotate this coil through 90 degrees? The new position is going to be let me use green. I think this is 90 degrees. The new position is going to be that. Now the new normal is going to be facing upwards like that. That's the new normal. So what I've done is actually rotating the coil itself through 90 degrees. So rotating the coil through 90 degrees from position 1 to position 2. Now, the normal I think is supposed to point downwards. This normal. downwards like that. So what is going to be the angle between the new normal, the green thingy, and the original field direction of the field? What is going to be that angle? What's going to be that angle? Between the field, which didn't change, and the new normal. Do you realize that angle is 90 degrees or so?
Yes, teacher. My concern is simple. Given your direction of rotation, which is clockwise, 90 degrees clockwise, so the angle will be the same, but the normal, will the normal be facing that way?
No, when you rotate this one, it comes downwards. Normal was like this. No, the normal goes through. For example,
Got it. It goes through.
that what?
Thank you, sir.
You
I've
got
got
it?
it. Yes, thank
Okay.
you.
Okay, so do you realize that now the angle between the new normal and the original direction of the field is also 90? So what does that mean? From our final now, our magnetic flux, final magnetic flux, which is NBA, the angle between the original magnetic field and the new normal, because the magnetic field direction didn't change, the new normal changed. The angle is 90 degrees, and you know cos of 90 is 0. Cos of 90 is 0. So that's why NBA here becomes 0. The magnetic flux density is a 0. So this is our final. When it is rotated through 90 degrees, that's our final. The change in magnetic flux, in case it is asked, you get initial minus final, and you get that answer. So what happens if it is rotated through 90 degrees? Through 90 degrees, the same knowledge, if you understood the same knowledge, we use the same knowledge to work out through 90 degrees to get how the angle is. So because our time is fast spent, maybe we can use the 5 minutes that we went off to take us through some simple thing, that is uniform and non-uniform magnetic field. Uniform magnetic field, compare these two fields. For example, if these are my field lines, yeah, this is, if these are field lines, oh, it's failing to come out the way I want it. Okay, what I
Excuse me,
want to
sir.
do, but I want to maintain these ones up to this point straight, then the rest can spread throughout. So the straight part is what we call the uniform magnetic field. Then the non-straight part is the non-uniform magnetic field. The straight one is the uniform magnetic field. The non-straight one is the non-uniform magnetic field. Okay, I'll add on something slight and then we stop at that. We've not gotten time to go through. We've gone through that current conductor. Maybe I'll just look at this and then we call it a day. That what happens, I know that when a conductor is carrying current into the paper, we use a circle and a dot. Out of a paper, we use a circle. No, into the paper, a circle and a cross. Out of the paper, a circle and a dot. So by now you should be knowing that into the paper from the grip right-hand rule or the Maxwell corkscrew rule into the paper and clockwise, like that. Out of the paper, clockwise, like that. So if I'm to combine these two, the field that I come up with is that. Now, on the other hand, if you have two fields combined and both of them are into the paper, we said into the paper is what? Clockwise. Hey, have I confused it? Out of the paper is anti-clockwise. I think this was supposed to be let me try it here. Into the paper, clockwise. Out of the paper, anti-clockwise. So a dot is anti-clockwise. A dot is anti-clockwise. Across is what? Across is clockwise. So where we have across into the paper, which is clockwise, we shall have our direction like that. Now this one will be like that. Now we are combining two fields of a current carrying conductor. Now I'm confusing them. Time. Let me draw it here as we wind up. So we said into the paper is anti-clockwise. I mean is clockwise like that. So what happens if these are to combine? They form something like that. Just joins the other one and comes back and eventually comes up like that. Now, where do we apply this? Someone would ask, where is this applied? This is a neutral point. I hope you have seen two wires carrying electricity from one electric pole to another. Have you seen that? Two wires carrying electricity from one electric pole to another. Sometimes they carry current in opposite direction, sometimes they carry current in the same direction. But it is important that you don't affect the distance, because the distance between those wires, that 1 meter distance, is perfectly calculated. Otherwise, there is a force of attraction or repulsion. Unlike in electrostatics, in magnetism for us, like charges attract, unlike charges repel. I think I want to leave you with that. In magnetism, like charges attract each other, unlike charges repel. That's a difference with electrostatics. So that's why when these two wires are carrying electricity from one pole to another in the same direction, there is a force of attraction. So once you tamper with those electric wires, remember they are bare. Once you tamper with them, you reduce on the space between them. The force of attraction becomes stronger, so they combine and an electric shock is observed. So it is important not to tamper with them. Okay, I want us to stop here for now. Just one word from one person and then a prayer. We call it a day.
Teacher, we appreciate your work. And teacher, I would like to ask, where are we going to get the video?
Mr. Kaziwa is going to share, don't worry. So this is work that we shall look at next time. I thought we could cover it all at once today, but we shall look at it next time. Mr. Kaziva is going to share all that we have.
Okay, humble yourselves for a concluding prayer. Dear Heavenly Father, we thank you for this wonderful moment that we have been with. Please, Lord, keep us safely when we are going through the weekend. Keep our teachers safe. Please guide them on what they are teaching us and help us to acknowledge all the work that they are teaching us. In Jesus' name we have prayed.
Amen. Kale, thank you so much. Have a nice time, guys.
I would like you to send us the notes as well.
Okay, we shall get
And
them.
I would also like to ask when will the next lesson be?
Same time, same day.
Okay, thank you, sir.
Welcome.
Thank you, sir, for the lesson.
Welcome.
Teacher,
Yes.
thank you for the lesson. I would like to inquire, can't we get an extra lesson?
Extra lesson, I don't know, because my schedule is very tight.
Okay, thank you, sir.
Maybe you can just take a number. I share some content or some material.
Teacher, I would like to ask, can I meet you in person and you help me with some numbers here? Like on WhatsApp.
Good evening, sir.
It's a bit tricky.
Good evening, sir.
Teacher, are we only focusing on magnetism? Okay.
Kale, friends, I want to wish you a blessed evening. But
Teacher,
share
the number.
Teacher, the number.
Teacher, the number.
Number.